day to all of you. So we're already finished with chapter 9, which is all about main memory. So now we are already in chapter 10, virtual memory. So in this lesson, we will differentiate between the main memory and of course our topic is virtual memory. How different is virtual memory from main memory? So why it's called virtual? Is it really like main memory, which is a chip, or is it another type of device or medium? So let's start our lesson with virtual memory. Again, chapter 10 is all about virtual memory. So the contents of chapter 10 are background, and then we have demand paging, copy on write, page replacement, allocation of frames, thrashing, memory mapped files, allocating kernel memory, other considerations, and operating systems examples of their implementation about virtual memory. So the objectives of this chapter are define virtual memory and describe its benefits, illustrate how pages are loaded into memory using demand paging, apply the FIFO or the first in first out, optimal, and LRU or the least recently used page replacement algorithms. Describe the working set of a process and explain how it is related to program locality. Describe how Linux, Windows 10, and Solaris manage virtual memory, and design a virtual memory manager simulation in the C programming language. So for the background for this lesson, so code needs to be in memory to execute, but entire program rarely used. So what are these codes? This can be error code, unusual routines, and large data structures. So the entire program code not needed at same time. So consider ability to execute partially loaded program. As you can remember with chapter 9, main memory. So not not the entire process is needed to be loaded in memory. Only some parts that truly needs the resources for memory. So it's just the same with this one. So because of the systems has already the ability to execute partially loaded program, so program no longer constrained by limits of physical memory. So other advantage is each program takes less memory while running, so more programs run at the same time. So what are the benefits? So increased CPU utilization and throughput with no increase in response time or turnaround time. And then next is we have less I/O needed to load or swap programs into memory. So each user program runs faster for the benefit. So virtual memory. So virtual memory is a separation of user logical memory from physical memory. So only part of the program needs to be in memory for execution. Logical address space can therefore be much larger than physical address space. So allows address spaces to be shared by several processes, allows for more efficient process creation, so more programs running concurrently, and less I/O needed to load or swap processes. So we can consider virtual memory. So in a typical computer system, actually the free space on your hard drive can be used as virtual memory. So as to why those who are familiar with Windows, if your hard drive has already less space, because the system, the Windows for example, is allocating this particular free space, this amount. So for example, if your hard drive, for example, has reached the threshold of the free space, there's a message of the system that's saying that the virtual memory is too low because the free space in your hard drive is already too low. So it is advised that you delete files that you don't need anymore or uninstall programs that you rarely use. So that the problem is, for example, if you have the space that is needed for virtual memory is already too small, it will affect the overall performance of your computer system. So virtual address space, this is the logical view of how process is stored in memory. Usually start at address 0, contiguous addresses until end of space. Meanwhile, physical memory organized in page frames. So the memory management unit must map logical to physical. So virtual memory can be implemented via the demand paging and demand segmentation. So the virtual memory that is larger than physical memory, of course, if you're going to use the free space of your hard disk as the virtual memory, it is really relatively bigger than the physical memory that you have. So for example, we have virtual memory from page 0 until page V, and then it has a corresponding memory map, and then this memory map has a corresponding addresses in physical memory. And of course, the memory map is connected to the backing store, and also the physical memory is also connected to the backing store. So virtual address space. Usually design local logical address space for stack to start at max logical address and grow down. So the stack grows down while the heap grows up. So that's why we have an arrow here for stack. It grows down and then the heap grows up. So it maximizes address space use. Unused address space between the two is a hole. So this is the hole. So no physical memory needed until heap or stack grows to a given new page. And then enable sparse addresses or scattered address spaces with holes left for growth, dynamically linked libraries and others, and then system libraries shared via mapping into virtual address space, and then shared memory by mapping pages read-write into virtual address space, and pages can be shared during fork, system call, speeding process, creation. So shared library using virtual memory, of course, if you're having shared library, so there should be the same pages that this shared library is accessing. Okay, next is we have demand paging. Could bring entire process into memory at load time, or another is bring a page into memory only when it is needed. So the benefit of that is less I/O needed, no unnecessary I/O, less memory needed, faster response, and more users. Similar to paging system with swapping. So we'll see the diagram later. Then if the page is needed, you need a reference to it. So if it's an invalid reference, then you have to abort. And when it's not in memory, bring it to the memory. So we have this lazy swapper, never swaps a page into memory unless page will be needed. So swapper that deals with pages is of course called a pager. So this is this is the demand paging, and it is said that could bring entire process into memory at load time. So for example, we have program A, then it needs to be swapped out going to the backing store, and then program B, which needs three um, uh, pages or frames for the main memory, will be swapped in. Okay, next is we have basic concepts. So with swapping, pager guesses which pages will be used before swapping out again. Instead, pager brings in only those pages into memory. So how to determine that set of pages? So need new MMU functionality to implement demand paging. If pages needed are already memory resident, so no difference from non-demand paging. So if page needed and not memory resident, need to detect and load the page into memory from storage. So how are we going to do that? So it's either without changing program behavior and without programmer needing to change code. So as like with the chapter 9 main memory, it also has valid and invalid bit. So with each page table entry, a valid invalid bit is associated. So if V, it's in memory or memory resident, or I, not in memory. So initially valid invalid bit is set to I on all entries. So it's not in memory. So example of a page table snapshot. So it means this 3 is already in memory while I is not yet in memory. During MMU address translation, if valid invalid bit in page entry is I, there is a page fault. So we have page table when some pages are not in memory. So for example, we have logical memory. Their page is, so this is page 0. So A, so it is in frame number 4. So it's already in memory. And then we have 2, which is in frame 6. So again, so it's clearer. Okay, so that's why it's in here. So um, page 0, so we have A, so it's stored in frame number 4. And then we have 2, which is C. It's stored in frame number 6 in the physical memory. Then we have 9, or rather, we have here 5, which contains F, so it will be stored in frame number 9. Okay, so it means that 4, so we have A, C, and F are already in memory, so that's why their valid invalid bit is V, while the others, it's not yet in memory, so that's why it's still I. So next is steps in handling page fault if the page is not yet in memory. So if there is a reference to a page, first reference to that page will trap the operating system, which is why it's called page fault. So operating system looks at another table to decide. If it's an invalid reference, then abort. So maybe it's not just really in memory. So number 3 is find free frame to store the page, and then swap page into frame via scheduled disk operation if, for example, the frames are full. And then number 5, reset tables to indicate page now in memory, then set validation bit is equal to V, and then restart the instruction that caused the page fault. So these are the steps in handling page fault with illustration. So we load M, and then it has a reference here. And what if there is no there's the page that is needed is not yet in the page table, so it will be invalid. So there's a trap in the operating system, and then the operating system will fetch the page on the backing store, and then number 4, it will be brought the missing page to the physical memory. Okay, in the free frame, if there is free frame, or if there is no free frame, you have to swap out a page. And then next is, after that is, we have to reset the page table, and then restart instruction. So since already the page is already brought to the page table, the valid invalid bit will be V in this case. Okay, next is we have aspects of demand paging. So the extreme case is start process with no pages in memory. So OS sets instruction pointer to first instruction of process. So if non-memory resident, then there will be page fault. And for every other process pages on first access. So on every first access, or there is no pages in memory, it's always a page fault. So we have this term pure demand paging. So never bring a page into memory until it is required. So that is the definition of pure demand paging. Then actually, a given instruction could access multiple pages, so we have multiple page faults. So consider fetch and decode of instruction, which adds two numbers from memory and stores result back to memory. So pain decreased because of locality of reference. So locality of reference is the tendency of processes to reference memory in patterns rather than randomly. So you can see an illustration of locality of reference later on this chapter. And then we have hardware support needed for demand paging. So page table with valid invalid bit. Then we have secondary memory, swap device with swap space, and instruction restart. So for the instruction restart, so consider an instruction that could access several locations. So we have block move. So it can auto increment or decrement location. So what if the source and destination overlap? Would we restart the whole operation? So if the source and destination blocks overlap, the source block may have been modified, in which case we cannot simply restart the instruction. So for blocking as much as possible, we have to avoid the source and destination overlap, because the source, because it has overlap the source, maybe the code of the source will be is already modified. So again, it's not easy to restart the whole operation or the instruction. So next is we have free frame list. So when a page fault occurs, the operating system must bring the desired page from secondary storage into main memory. So that's why the secondary storage, the one of the actual devices for categorized as secondary storage is the hard disk. And then most operating systems maintain a free frame list, a pool of free frames for satisfying such requests. So this is the illustration. 797, 1520, 126 to 75. These are all the free frames that is of course in the list. So operating system typically allocate free frames using a technique known as zero fill on demand. The content of frames zeroed out before being allocated. It means if this free frames list will be used again, so their contents, their previous contents will be erased for security purposes. So when a system starts up, all available memory is placed on the free frame list. Okay, next is stages in demand paging, the worst case. So number 1 is trap to the operating system. Number 2, save the user registers and process state. Number 3, determine that the interrupt was a page fault. Number 4, check that the page reference was legal and determine the location of the page on the disk. Number 5, issue a read from the disk to a free frame. So step number 5 is divided into three steps. Number 1, wait in a queue for this device until the read request is serviced. Number 2, wait for the device seek and or latency time. Number 3, begin the transfer of the page to a free frame. Okay, let's continue. Number 6, while waiting, allocate the CPU to some other user. Number 7, receive an interrupt from the disk I/O subsystem for I/O to be completed. Number 8, save the registers and process state for the other user. Number 9, determine that the interrupt was from the disk. Number 10, correct the page table and other tables to show page is now in memory. Number 11, wait for the CPU to be allocated to this process again. And then number 12, restore the user registers, process state, a new page table, and then resume the interrupted instruction. So performance of demand paging. So three major activities. Number 1 is service the interrupt. Careful coding means just several hundred instructions needed. Then next is read the page. So it takes a lot of time. And then restart the process again, just a small amount of time. So page fault rate is 0 is less than or equal to P is less than or equal to 1. If P is equal to 0, this is very lucky because there are no page faults. But if P is equal to 1, every reference is a fault. So we also have, just like in main memory, we have effective access time. So as you can remember, effective access time on using TLB, hit and miss. So EAT is equal to 1 minus P times memory access, and then plus P, and then the page fault overhead, plus swap page out, and plus swap page in. So that's the formula of effective access time for the demand paging. Okay, demand paging example. For example, so we have given variables here. So we have memory access time is 200 nanoseconds. And then the average page fault service time is equal to 8 milliseconds. So EAT is equal to 1 minus P times 200 plus, so we have the average page fault service time. So this is the 8 milliseconds. So we have then 1 minus P times 200 plus P times, we have 8 million. So this will be converted. And then next is we have 200 plus P times 7,999,800. So this will be our example. So if one access out of 1,000 causes a page fault, then 80 is equal to 8.2 microseconds. So how does this happen? This 8.2 microseconds. So again, let's have a calculator to show you how does 8.2 derived. Okay, so again, our calculator. Okay, so we have this one. So let's already start here. So, okay, so 200 plus P. So, of course, we have to apply, of course, M does here. So, P times 7,999,800. So, it says here, if one access out of 1,000 causes page fault, then, so our P here will be this one. 1 divided by 1,000. So we have 0.001 and then multiply it with this will be our P. Then multiply it with times 7,999,800. So okay, we'll get 7,999.8. And then this 7,999.8 plus 200. So that's why we have 8,199.8. So if you're going to convert it into microseconds, so we will have 8.2 microseconds. So move the decimal point to the left, 1 2 3, then just round it off. So that's why 8.2 microseconds. So this is a slowdown by a factor of 40. So why does this how does this 40 is derived? Okay, so if we're going to convert 8,199 to, since this is in 8.2 is in microseconds. So let's convert it into, okay, just remember 8199.8. So we have 0.00000819998. So that is in seconds. So microseconds is -6. So this will be in seconds. So let's subtract the 200 nanoseconds. So we have 0.0. Okay, how many zero is that? 1, 2, 2, 3, 4, 5. And then we have 200. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. Another 0. Okay, so we have that. Okay, so our result is we have this value. Then after we get this value, we have to divide it to 200 nanoseconds. So divided by, again, by 200 nanoseconds, 0.6 zeros. and then 200. So that's why we have 39.99. So that's why this is the result, why this is a slowdown by a factor of 40. Okay. So next is if the performance if our system, you want to have a performance degradation of less than 10%, so we have 220 greater than 200 plus we have this one 7,999,800 times P. Okay, how did we derive 220? It's because the 10% of 200 is 20 and then you add it to 200, so that's why it becomes 220. And then next is we have 20. So what happens here is that 200 is transferred to the left. So that's why 220 minus 200 is equal to 20 greater than 7,999,800 times P. Okay. So what are we going to do here? So we have to get P, we have to divide it by 7,999,800. So, okay, if we're going to divide 20 divided by 7,999,000, then 800. Okay, so that's 2.5. So, since that we want it to be, because this is -6, you have to adjust it. So, it will be, so that's why 2.5. So, 1, 2, 3, 4, 5, 6. So, to remove this -6 here. So, we have P is less than 0.000000025. So, less than 1 page fault in every 400,000 memory accesses. So, that is to keep the slowdown due to paging at a reasonable level. We can allow fewer than one memory access out of 399,992 page fault. Okay, so this is how we solve the demand paging with given for memory access time and average page fault service time. Okay, next is demand paging optimization. So, swap space I/O faster than file system I/O even if on the same device. So, swap allocated in larger chunks, less management needed than file system. So, copy entire process image to swap space at process load time, then page in and out of swap space. So, these are used in older BSD Unix. And then there's another one, demand page in from program binary on disk, but discard rather than paging out when freeing frame. So it is used in Solaris and current BSD. So still need to write to swap space. So pages not associated with a file like stack and heap, we have the so-called anonymous memory. So pages modified in memory but not yet written back to the file system. So for mobile systems, they typically don't support swapping as like with the discussion with the main memory. So instead, demand page from file system and reclaim read-only pages such as code. So next is we have the copy on write or COW. Allows both parent and child processes to initially share the same pages in memory. If either process modifies a shared page, only then is the page copied. So COW allows more efficient process creation as only modified pages are copied. In general, free pages are allocated from a pool of zero fill on-demand pages. So pool should always have free frames for fast demand page execution and don't want to have a free frame as well as other processing on page fault. So why zero out a page before allocating it? It is already answered in the previous slides because it's necessary, it's for security protection. So that's why for before allocating it, the page should be empty. So we have V fork variation or on fork, so virtual fork. This is a system call, has parent suspend and child using copy on write address space of parent. So designed to have child call the exec system call, and it is very efficient, the usage of v-for. So before process 1 modifies page C, so of course, this processes share page A, B, and C. So because of copy on write, so once page C is modified, so by the process 1, so it will copy a page of C. So that is the meaning of copy on write once page C is modified. So what happens if there is no free frame? So of course, it is used up by process pages, also in demand from the kernel, I/O buffers, and others. So how much to allocate each? So if there is no free frame, we have this page replacement. Find some page in memory but not really in use and page it out. So how is the algorithm? Are we going to terminate it, swap out, or replace the page? So somewhat it's more of page replacement. Then performance, want an algorithm which will result in minimum number of page faults. Same page may be brought into memory several times. So page replacement. So prevent over allocation of memory by modifying page fault service routine to include page replacement. So use modify. So another term for modify here in the bit is dirty. So for the dirty or modify bit, to reduce overhead of page transfers, only modified pages are written to disk. And then page replacement completes separation between logical memory and physical memory. Large virtual memory can be provided on a smaller physical memory. So need for page replacement. So for example, so for the program counter, so logical memory for process 1, and then it is here, it will be loaded in the page table for process 1. So since it is invalid, since it is still empty, but once it is already in the page table, it will be valid. So after that, from the backing store, the data B will be fetched, and of course, if physical memory is already full, which of this data will be swapped out? So that's a question. Okay. So this is an example for need for page replacement if physical memory has no free space. So basic page replacement. So find the location of the desired page on disk and then find a free frame. If there is a free frame, then of course use it. If there is no free frame, use a page replacement algorithm to select a victim frame. So write victim frame to disk if dirty or modified. And then number 3, bring the desired page into the newly free frame, update the page and frame tables. And then number 4, continue the process by restarting the instruction that caused the trap. Note now, potentially 2 page transfers for page fault. So increasing effective access time or EAT. So page replacement, for example, so in the page table, so we have, this is the first. So swap out victim page. And then number 2, change to invalid since you've removed the victim page. And then number 3, swap desired page in the physical memory. And number 4, reset page table for new page. So we need to update the page table for it to be correct for accessing, of course, the backing store and for the physical memory. So there are no errors. So again, if we swap out the victim page, you have to change its allocation in the page table to invalid, and then we're going to swap another page in place of the victim page, and then of course we're going to reset and update the page table. So we have page and frame replacement algorithm. So frame allocation algorithm determines how many frames to give each process and then which frames to replace. And then we have page replacement algorithm. So want lowest page fault rate on both first access and re-access. and evaluate algorithm by running it on a particular string of memory references or reference string and computing the number of page faults on that string. So string is just page numbers, not full addresses. So for page replacement algorithm, repeated access to the same page does not cause a page fault, especially if the page is already in memory. So results depend on number of frames available. In our all examples, the reference string of reference page numbers is this one. So this reference string. So graph of page fault versus number of frames. Of course, um, the higher the number of frames, the lower will be the page fault. That is ideal. So of course, if your number of frames is low in number, so there is a tendency there are higher page faults. So again, our first page replacement algorithm is called first in, first out. So what we're going to illustrate here are the common page replacement algorithms that are used in a computer system. So of course, one of this is the FIFO, or again, first in, first out algorithm. So this is the given reference string, and then our frames is 3 frames. So 3 pages can be in memory at a time per process. So that's why it's 3. Okay. Every change in the frame is a page fault. So we have 7 and then 0. So that's why 7 0 and then 7 0 1 and then 2, since first in, first out. So among 7 0 1, 7 is the first to be put or in the line. So that's why, since first in, first out, 7 is replaced by 2. And then 0, there is no page fault because 0 is already in the frame. Okay, then we have 3. Okay, so 3, as you can see, first in, first out, 7 is already removed. Then the next is 0. That's why 0 is replaced by 3. So that's why the number is 2 3 1. And then next is we have 0 again. So 7 0 1. So that's why 1 is replaced by 0. So we have 2 3 0. Okay, next is we have 4. So that's why 2 is replaced by 4. And then 4 3 0. And then next is we have 2. So we have, which of them is replaced? 7 0 1, then 2, and then we have which is replaced. Okay, so actually for this example, so if you're going to follow the algorithm, so you have to continue. The technique here is just to remove the first in line. Okay, so if you're going to continue until you end it here, so we have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So we have 15 page faults. Actually, I will provide an additional video. I don't know if it's easier, but for me, in my opinion, I have other ways on how to determine the page replacement algorithm, not by using frames, but of course the result is will always be the same, which is also 15. Okay, so please watch out for that additional video to do it manually. How to do this page replacement algorithm? It is applied to all the page replacement algorithms given here. So the results can vary by reference string. So consider this string. Okay, if it's 3 frames, actually, you will have a result of I've already done this. I will show you again. Separate from first in, first out. So to see if it is 3 frames, you will have 9 page faults as a result. But the odd thing here is, if you do it with 4 frames, do you know how many page fault it is? It is 10 page faults. So you're going to wonder, because as you can see, if you increase the number of frames, of course, logically, it will lower the number of page faults. As to why is it in this string, this reference string, adding another frame will it has a tendency to increase the page fault. So that's why adding more frames can cause more page faults, and it's called Beladi's anomaly. So I'm going to show you if it's 3 frames, it's 9 page faults, and then if it's 4 frames, then it became 10 page faults. So how to track ages of pages? So just use a FIFO, or again, first in, first out queue. Okay, so this is a graph that illustrates the Biladis anomaly. So again, it depends upon the reference string and the sequence. Okay, next is we have the optimal algorithm. So replace page that will not be used for longest period of time. So it means that, so for this example, 1, 2, 3, 4, 5, 6, 7, 8, 9, the same reference string, but because you use optimal, so from 15, it only became 9. So what's the technique for optimal algorithm? So for example, again, so 701, 701, and then we have 2. Okay, what you're going to do now is, why it's 7? Okay, 701. Look here. It's like this. You have to look to the future, to the reference string. Among 701, which among this is to be used later? The latest, or rather, will not be used for a long period of time. So here 7, okay, the instance of 7 is here, and then next is 0. You can see it will be used next, so you can't replace that. And then 1 is where? Here. So it means 7 will be used for the longest period of time, so you have to replace 7 by 2. And then, of course, there's no page fault because 0 is here. Okay, next is 3 again. So, 201, the given is 201. So, where is 2? So, this is 2, this is 0, and where is 1? Since 1 will not be used for a long period of time, so as you can see here, 1 is replaced by 3. So, that's the technique of optimal algorithm. So, for the given pages here, you have to determine which of them will not be used for a long period of time. Okay, so how do you know this? So, can read the future. So, this is used for measuring how well your algorithm performs. So, this is advantageous if you already know the reference string. Okay, I'll provide again a video for this, for how to do it manually. Okay? Okay, then the third one is we have the least recently used, or LRU algorithm. So use past knowledge rather than the future. And then replace page that has not been used in the most amount of time. So, associate time of last use with each page. Okay. If optimal algorithm looks into the future with in the reference string to the right, least recently used is you're going to look to the left. So, again, we have 701. So, then next is 2. So, among this one, which is the least recently used? Okay, because the list is we have 7, so that's why it is replaced by 2. And then 0, there's no page fault because 0 is already in the frame. Okay, next is 3. So our given here is 201. So 201, which of them is least recently used? Actually, it's 1, so that's why it is replaced by 3. And then 0 is already here. So next is we have 4. So 203 which of them is the least recently used. Actually, it is 2. That's why you will replace 2 with 4. And then just follow the algorithm for least recently used until you get the total, all the references in the frame. So we have 12 faults. So actually, it's better than FIFO but worse than optimal. Because FIFO is what? 15. Actually, it's in the middle. And optimal is, we have 9 page faults. Okay. So, generally good algorithm and frequently used. But how to implement? Since we're looking at the past. Again, least recently used, you're going to look to the left, while the optimal is you're going to look to the right of the reference string. Okay, and of course, I'm going to provide again another way to get uh, to manually do the least recently used algorithm. So, how to implement is we need to have a counter. So, every page entry has a counter. Every time page is referenced through this entry, copy the clock into the counter. When a page needs to be changed, look at the counters to find smallest value. Then search through table needed. And then we could also have, aside from counter, is we can do it with a stack implementation. Keep a stack of page numbers in a double link form. So page reference, move it to the top. Requires 6 pointers to be changed. So that's the problem with stack. It's because it's expensive because you need 6 pointers. But each update more expensive. So no search for replacement. So LRU and optimal are cases of stack algorithms that don't have Beladis anomaly. Only FIFO has this Beladis anomaly. So this shows how to use a stack to record most recent page references. For example, so we have 4. So the first is, we have in a stack, of course, you have to put it below. So 4, 7, 0, we have again 7, it's already here, and then 1, and then 0 again, it's already here, then 2. Okay, so stuck before A. Okay, then we have 1 and 2. So for this one, why is it it is said that if we already have the values, it should be moved to the top. Since it's not yet full, so that's why there is no movement in the, for example, 4, 7, 0, 1. So 0, and then 1, 2, and then 1, 2 again, and then before, then B. So what happens, since 7 is already accessed, so that's why from here 7 is moved to the top, because this is the recently used page. Okay, next is we have LRU approximation algorithm. So LRU needs special hardware and it's still slow. So we need to have a reference bit with each page associated a bit initially 0. When page is reference bit set to 1, replace any with reference bit is equal to 0 if 1 exists. So we do not know the order, however. Then we also have this second chance algorithm. So generally, FIFO plus hardware provided reference bit. Then it can use clock replacement. If page to be replaced has reference bit is equal to 0, then replace that page. And then reference bit is equal to 1, then set reference bit 0, then leave page in memory. Then after that, replace next page subject to same rules. So we have an illustration here. So for example, so this is 0, then the next victim supposedly is 1, since the rule is if it is 1, then you have to change it to 0, and then of course change it to 1. Then this next is you have to change it to 0 again, and then this is the next victim since it's already 0. This is the illustration for second chance or clock page replacement algorithm. So, how to enhance the second chance algorithm? So improve algorithm by using reference bit and modify bit if available. So in concert. So take ordered pair. So ordered paired, we have this first is for reference and next is for modify. So 00, neither recently used, not modified, best page to replace if this is the case. Then 01, not recently used but modified, not quite as good, must write out before replacement. So 10, it is recently used but clean. It's not yet modified. Probably will be used again soon. And then we have recently used and modified. Probably will be used again soon and need to write out before replacement. So when page replacement called for, use the clock scheme but use the four classes. These four classes replace page in lowest non-empty class. So this will only, it might need to search circular queue several times. So, aside from the most common, actually the most common page replacement algorithms are the FIFO, the optimal, and the LRU. But there are also counting algorithms. So, keep a counter of the number of references that have been made to each page, but this is not common. So, these two counting algorithms are the least frequently used, or LFU algorithm, replaces page with smallest count, and we also have the most frequently used MFU algorithm. So this is wrong spelling, should be T. So MFU, based on the argument that the page with the smallest count was probably just brought in and has yet to be used. We cannot provide examples as of this time because, of course, as I've said, these two are not commonly implemented in operating systems. Okay, next is we have page buffering algorithms. So keep a pool of free frames, so always, and then frame available when needed, not found at fault time. Read page into free frame and select victim to evict and add to free pool. Then when convenient, evict victim. So possibly keep list of modified pages. When backing store otherwise idle, write pages there and set to non-dirty. Then possibly keep free frame contents intact and note what it is in them. Then if reference again before reuse, no need to load contents again from disk. And generally useful to reduce penalty if wrong victim frame selected. So applications and page replacement. So all of these algorithms have OS guessing about future page access. Some applications have better knowledge such as databases. So memory-intensive application can cause double buffering. So we have OS. So what is how this double buffering happens? So it's because OS keeps copy of page in memory as IO buffer, and application keeps page in memory for its own work. So operating system can give direct access to the disk, getting out of the way of the application. So this OS giving direct access to the disk is the raw disk mode. So it also bypasses buffering, locking, and others. So next is we have allocation of frames. So each process needs minimum number of frames. So example, for IBM 370, 6 pages to handle SS move instruction. So instruction is 6 bytes, might span 2 pages. And then 2 pages to handle from, and then 2 pages to handle to. So that's why it needs 6 pages. So maximum, of course, is the total frames in the system. And then two major allocation schemes. We have the fixed allocation and priority allocation, and it has many variations. So we have fixed allocation. So we have two types of fixed allocation. It can be equal allocation or proportional allocation. So for example, if there are 100 frames, after allocating frames for the OS and 5 processes, give each process 20 frames. So it doesn't matter if the process is small or big or large. So if equal allocation, just divide 100 divided by 5 is equal to 20. So keep some as free frame buffer pool. So what about proportional allocation? So allocate according to the size of the process. So dynamic as degree of multi-programming process sizes. For S sub I, The small s sub I is the size of process P sub I, and then S is the summation of the size of the processes, S sub I. M is the total number of frames, and then A sub I is allocation for P sub I is equal to small s sub I over S times M. So for this example, okay, it's a correction. It should be 62. So our M here, our total number of frames is 62. And then the size of process 1 is 10. And then the size of process 2 is 127. So if proportional allocation, it means you can predict that S sub 2 must have more um, frames than S sub 1 because of its size. So how to get the allocation is we have A sub 1. For A sub 1, for process 1 is we have, this is the size 10, then divided by 137. How did we get 137? Of course, it's because 10 plus 127, the sum of the sizes of all the processes. 137 times, so the total number of frames, which is 62, which is equivalent to or approximately equal to 4. So it means for process which the size is 10, 4 frames will be allocated. And then how about process 2? So again, so the size is 127 divided by 137 times 62 is approximately 57. Okay. It means that of course the larger the um, the larger the size of the process, it will allocate uh, more number of frames. But if you're going to add 57 plus 4 is we have 61. So you can conclude that there's another frame that is kept as a free frame. Okay. So that is the fixed allocation, equal or proportional allocation, and with the formula for proportional allocation. So next is we have global versus local allocation. So global replacement, process selects a replacement frame from the set of all frames. One process can take a frame from another, but then process execution time can vary greatly, but greater throughput, so more common. So more common to be used. So how about local replacement? So each process selects from only its own set of allocated frames. So more consistent per process performance, but possibly underutilized memory. So next is we have reclaiming pages. A strategy to implement global page replacement policy. All memory requests are satisfied from the free frame list rather than waiting for the list to drop to 0 before we begin selecting pages for replacement. So instead of waiting for the free frames to drop to 0, so if there is, for example, a threshold, then it should begin selecting pages for replacement. Then page replacement is triggered when the list falls below a certain threshold. So this strategy attempts to ensure there's always sufficient free memory to satisfy new requests. So that's why, so they will never, there is only a threshold. If the threshold is already too low, it will start selecting pages for replacement. It will not let the memory be full. Okay, so we have reclaiming pages example. So for example, for this point, if the pages is minimum threshold, the kernel resumes reclaiming pages for this point A and point C, so that it will not never be under the minimum threshold. But for example, if for point B and point D, if there's already it already reaches the number of pages, the maximum number of pages, so kernel suspends reclaiming pages. So there we have, here is the minimum and maximum threshold. So next is we have non-uniform memory access. So far all memory accessed equally. So many systems are NUMA, or non-uniform memory access. So speed of access to memory varies. So consider system boards containing CPUs and memory interconnected over a system bus. So you've already seen this in our previous lessons. So NUMA, for example, we have 4 CPUs, then they are interconnected, and then they have their own set of memory. So optimal performance comes from allocating memory close to the CPU on which the thread is scheduled. So, and modifying the scheduler to schedule the thread on the same system board when possible. So, solved by Solaris by creating L groups or locality groups. So, structure to track CPU or memory low latency groups. So, they use their own schedule and pager. So, when possible, schedule all threads of a process and allocate all memory for that process within the L group. So, next is we have thrashing. So, if a process does not have enough pages, the page fault rate is very high. So, page fault to get a page and then replace existing frame, but quickly need replace frame back. So, this leads to low CPU utilization. So, because of low CPU utilization, the operating system thinks that it needs to increase the degree of multi-programming. So, what happens is another process added to the system. So, thrashing. So, what is thrashing? A process is busy swapping pages in and out. So, that is the problem. So, what causes a thrashing? Because of this thrashing, there is low CPU utilization. So, the solution for at this point, for example, you already have a definite, relatively higher CPU utilization, but because of thrashing, CPU utilization will become low. So how to increase the CPU utilization and stop thrashing is you have to decrease the degree of multi-programming. That's the solution. Okay, so that's why it's in here. So for this illustration. So next is demand paging and thrashing. Why does demand paging work? So it's because of locality model. So process migrates from one locality to another and then localities may overlap. So why does thrashing occurs? So because the total size of locality is greater than the total memory size. So actually the cause of thrashing is that it is already defined that the CPU is busy swapping pages in and out. It's not doing its own job to manage, of course, the processes. So it's just busy swapping in pages in and out of the memory. So limit effects by using local or priority page replacement. So we have a locality in a memory reference pattern. As you can see, if there's a locality in the memory reference, because as you can see, it is said that locality reference means that the 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 access to memory is in pattern, not randomly. So for example, if you use, for example, this memory here, then you're going to access memory that's adjacent to this place. So that's why you can get more of the idea of because of the locality reference. Okay, next is we have the working set model. So we have a symbol here. It's actually delta. So delta, so it is the working set window, a fixed number of page references. So for example, we have 10,000 instructions. So we have WSS sub I, or working set of process P sub I, is equal to the total number of pages referenced in the most recent working set window, which varies in time. And then if delta is too small, it will not encompass entire locality. If the delta is too large, it will encompass several localities. And if delta approaches to infinity, it will encompass the entire program. So, D is equivalent to the summation of all the working set processes of P sub I, or the total demand frames. So, demand is the approximation of locality. So again, if D is greater than M is the total number of available frames, it will cause thrashing. So policy, if D is greater than M, suspend or swap out one of the processes. So keeping track of the working set. So approximate with interval timer plus a reference bit. So example, our delta is 10,000. So timer interrupts after every 5,000 time units. And then keep in memory 2 bits for each page. And then whenever a timer interrupts, copy and sets the values of all reference bit to 0. And then if one of the bits in memory is equal to 1, then the page is in the working set. So why is this not completely accurate? Because of course, so we need to have an improvement. So for it to be accurate, so we have 10 bits and interrupt every 1,000 time units. So as to why it's not completely accurate, because this arrangement is because we cannot tell where within an interval of 5,000 a reference can be occurred. Okay, next is we have page fault frequency. So more direct approach than WSS, or the working set for process P sub I. So establish acceptable page fault frequency rate and use local replacement policy. So of course, page fault actually is inevitable, especially if there are no pages in memory. So if actual rate is too low, process loses frame. And then if actual rate is too high, process gains frame. So we have this one. So again, we have a threshold. We have the upper bound. So if the page fault rate increases beyond upper bound, so the system will increase the number of frames. But if the page fault is lower than of course, the lower bound, so of course, it doesn't need a number of frames. So it will decrease the number of frames if the page fault rate is lower than the lower bound. Okay, next is we have memory compression. So memory compressions, rather than paging out modified frames to swap space, we compress several frames into a single frame, enabling the system to reduce memory usage without resorting to swapping pages. So if it can be compressed to a single frame, the three, for example, pages, the better. So consider the following free frame list consisting of 6 frames. So 1, 2, 3, 4, 5, 6. And then we have the modified frame list. So assume that this number of free frame falls below a certain threshold that triggers page replacement. So the replacement algorithm, say an Lru approximation algorithm, selects 4 frames, which is 15, 3, 35, and 26 to place on the free frame list. It first places these frames on a modified frame list, so that's why it's in here. And then typically, the modified frame list would next be written to swap space, making the frames available to the free frame list. An alternative strategy is to compress a number of frames, so using m dash, say 3, and store their compressed version in a single page frame. So that's the meaning of memory compression. If 3 pages can be compressed in a page frame, in one page frame, 2 or more, the better. So, of course, this is memory compression is an alternative to paging. So, rather than paging out modified frames to swap space, we compress several frames into a single frame, enabling the system to reduce memory usage without resorting to swapping pages. So, for this example, so the uh, for the modified frame list, as we can see, 15, 3, and 35 is already gone. Actually, this is already in frame number 7. So that's why, for example, you do not need to swap page out. You can already access here, which is the frames. Again, we have 15, 3, and 35. It's already in this frame for compressed frame list. Okay, next is working sets and page fault rates. So direct relationship between working set of a process and its page fault rate. So working set changes over time because you can have a working set here, or it depends upon the setting. And then peaks and valleys over time. So next is allocating kernel memory. So treated differently from user memory, often allocated from a free memory pool. So kernel requests memory for structures of varying sizes. So some kernel memory needs to be contiguous, such as for device input, output. So next is we have body system. So allocates memory from fixed size segment consisting of physically contiguous pages. So memory allocated using power of 2 allocator. So 2, 4, 2, 4, 8, 16, 32, 64, 128, 256, and so on. But all powers of 2. So satisfies request in unit size as power of 2. Request rounded up to the next higher power of 2. When smaller allocation needed than is available, current chunk split into two bodies of next lower power of 2. Continue until appropriate size chunk is available. For example, assume that we have a 256 kilobyte chunk available and the kernel only requests 21 kilobytes. So what we're going to do? So you have to split 256 so into A, L, the left, and A sub R to the right. So it will become 256 divided by 2 is we have 128 kilobyte each. So it's still too big. So again, one further divide. So this is B. That's why B sub L and B sub R left and right. So 128 divided by 2 will be 64 kilobytes. So it's still big again. So one further into C, left and right. So 64 divided by 2 is equal to 32. So one used to satisfy a request. So this is already the where 21 kilobyte will be fitted, because if you still divide it into 2, it will have an answer of 16. 21 kilobyte is not fitted with 16, so it should be in the 32 kilobyte. So advantage, quickly coalesce unused chunks into larger chunk, meaning you can quickly combine because this is the body system. You have to, for example, if the kernel requests a small value, you just need to divide it by 2. And then the disadvantage, of course, is fragmentation. So this is our example for the body system allocator. So again, if you need a request, and then it should be a power of 2. So for our example, 21 kilobyte. So it fits per the with the smallest leftover hole is we have the 32 kilobyte. Then it is again, it is already illustrated that it's the always divided or split into 2. Okay, next is we have the Slob Allocator. So it's an alternate strategy. So slab is one or more physically contiguous pages. Then cache consists of one or more slabs. So single cache for each unique kernel data structure. So each cache filled with objects or instantiations of the data structure. So when cache is created, filled with objects marked as free. And then when structures are stored, objects marked as used. If slab is full of used objects, next object allocated from empty slab. So if no empty slabs, new slab is allocated. Benefits include no fragmentation, fast memory request satisfaction. So this is the illustration of a slab allocation. Then we have kernel objects, and these kernel objects are, their data is inside the cache, and then this cache has their own allocation in the slabs. Okay, Slab Allocator in Linux. So for example, process descriptor is of type struct task underscore struct. So approximately 1.7 kilobyte of memory. So for new task, allocate new struct from cache. So we'll use existing free struct task underscore struct. So slab can be in three possible states, which is full, which is all used, empty, all free, partial, mix of free and used. Upon request, the slab allocator, number 1, uses free struct and partial slab. Number 2, if none, takes 1 from empty slab. And then number 3, if no empty slab, create new empty. So Slab started in Solaris, now widespread for both kernel mode and user memory in various OSs. So Linux 2.2 had Slab, now has both Slob and Slob Allocator. So Slob for systems with limited memory. So Slab means simple list of blocks. So maintains 3 list objects for small, medium, large objects. While Slob is performance optimized slab, removes per CPU queues metadata stored in page structure. So unfortunately, I cannot find any meaning for slab, so only the slab, which is the simple list of blocks. So it's a performance optimized slab. So next is we have other considerations. So we have pre-paging, page size, TLB, which is translation look aside buffer reach, inverted page table, program structure, and IO interlock and page locking. So for pre-paging, so to reduce the large number of page faults that occurs at process startup. So that's why pre-paging is implemented. Pre-page all or some of the pages a process will need before they are referenced. So, but if pre-page pages are unused, so the problem is I/O and memory was wasted. So, assume S pages are pre-page and alpha of the pages is used. So, is cost S times alpha save pages faults greater than or less than the cost of the pre-paging S times 1 minus S unnecessary 1 minus alpha rather unnecessary pages. So if alpha is near 0, pre-paging loses, but if we have alpha near to 1, then pre-paging wins. Okay, next is we have page size. So sometimes OS designers have a choice. So especially if running on custom-built CPU. So page size selection rather must take into consideration. We have fragmentation, page table size, resolution, I/O overhead, number of page faults, locality, TLB size, and effectiveness. So it's always a power of 2, usually in the range of 2 raised to 12, which is 4096 bytes, or 2 raised to 22, we have 4,194,304 bytes. So on average, growing over time because of course, our hard drives are growing in size and also the capacity of our main memory. So next is we have TLB Reach. So the amount of memory accessible from the TLB. So the formula for TLB reach is the TLB size times page size. Ideally, the working set of each process is stored in the TLB. Otherwise, there is a higher degree of page faults. So increase the page size. So this may lead to an increase in fragmentation as not all applications require a large page size. So provide multiple page sizes. So this allows applications that require larger page sizes the opportunity to use them without an increase in fragmentation. So it's either increase the page size or provide multiple page sizes. So for the program structure, so we have this int 1 to 8. This is an array. So each row is stored in one page. So for program 1, so because of this for loop, so it will create, it's multiplied 128 times 128 is we have 16,384 page faults. So for program 2, what has happened? The for loop, it was exchanged. So why is it only 128 page faults? Because program 2 zeros all the words on one page before starting the next page, reducing the number of page faults to 128. So next is we have the I/O interlock. So I/O interlock, pages must sometimes be locked into memory. So Consider IO pages that are used for copying a file from a device must be locked from being selected for eviction by a page replacement algorithm, such as for this example, for our illustration. So, pinning of pages to lock into memory. So, for example, this drive is using this part of memory. It will be pinned for the meantime while the disk drive is using this part of memory. So, operating system examples of virtual memory. So, we have for Windows and Solaris. So, for Windows, uses demand paging with clustering. So, clustering brings in pages surrounding the faulting page. Processes are assigned working set minimum and working set maximum. So, working set minimum is the minimum number of pages the process is guaranteed to have in memory. Then, a process may be assigned as many pages up to its working set maximum. So when the amount of free memory in the system falls below a threshold, automatic working set trimming is performed to restore the amount of free memory. Then working set trimming removes pages from processes that have pages in excess of their working set minimum. So for Solaris, so maintains a list of free pages to assign faulting processes. So lots free, this is the threshold parameter or amount of free memory to begin paging. And then des free, threshold parameter to increasing paging. And then min free, threshold parameter to being swapping. So paging is performed by page out process. So page out scans pages using modified clock algorithm. Then scan rate is the rate at which pages are scanned. So this ranges from slow scan to fast scan. And then page out is called more frequently depending upon the amount of free memory available. So priority paging gives priority to process code pages. So this is the Solaris page scanner. So for min free, so it is fast scan, and then for des free, it's in the middle of min free and lots free. And then for lots free, it is a slow scan. So this is the end of our chapter for chapter 10, virtual memory. So I hope that you learned something, especially the page replacement algorithm. So how does virtual memory work? So what's the difference between main memory and virtual memory? So as I've said, I'm going to provide additional videos to illustrate how to do the three common page replacement algorithms, the FIFO, the first in, first out, the optimal page replacement algorithm, and the least recently used page replacement algorithm. So if you do have any questions, so please feel free to comment below. And of course, do not forget to like my and subscribe to my YouTube channel. So again, I hope that you've learned something about virtual memory. So thank you very much. Good day and stay safe.